Welcome to this video lecture. In this lecture, we are going to discuss temperature and how we describe temperature according to the kinetic theory of gases. So we're going to do a couple of things. We will look at temperature, what it is, and also how we measure temperature using thermometers. That is going to include the types of thermometers we use and actually how those work. Then we are also going to look at how a thermometer works, and that will bring us to the Zeroth Law of Thermodynamics. We'll see what that is. Basically, the Zeroth Law of Thermodynamics helps us to see if two objects A and B, are at the same temperature. So that's what we're going to do there. Next, we'll look at temperature scales. There are different types of thermometers, and those thermometers use different scales. So basically, we'll look at a liquid in glass thermometer. A liquid in glass thermometer actually has two different types of scales. You have some which have a scale which is in degrees Celsius, and there are some which have a scale which is in Fahrenheit. So we're going to see how that works. Then later on, we are going to introduce a special kind of thermometer, which is a constant volume gas thermometer. And these ones actually use a different scale, which is known as the Kelvin Scale. So we'll see how you come about with such scale. Then last but not least, at the end somewhere here, we are going to introduce the ideal gas law. We'll come up with the equations for the ideal gas law, and later on we'll come up with the expression for the ideal gas law, which we have here in equation 9. Then last but not the least, we are going to look at something known as the kinetic theory of gases. Basically, this kinetic theory of gases is a model we use to explain temperature. So we are going to see how we can use the kinetic theory of gases to explain what temperature is. So basically, in a nutshell, that is what our discussion is going to look like. Okay, and we have 15 pages to go through. So let's go back and see where we are going to start from. Okay. Yeah, it will take us a while. I think an hour or slightly more than an hour to go through this material. Okay. But I'll try to be as precise and also as brief as possible. Okay, so as you are aware from the beginning, temperature is one of the 7 SI base quantities. Okay, so it is quite very important in physics. Okay, and how do we define temperature? So basically, temperature in a nutshell, or in a layman's terms, temperature is the degree of hotness or coldness. That's what temperature is. Okay, and when you are talking about temperature, usually you are interested in the temperature of something. You are not interested in the temperature of each and every object which is in your sight. When you're talking about temperature, you are interested in the temperature of some specific objects. That specific objects whose temperature you are interested in is what we refer to as a system. Okay? The specific object, that portion of matter you are interested in, that's what we refer to as a system. In thermodynamics, there will be some thermodynamics which will come after this, but you, right from the word go, you should understand that when we are discussing temperatures and the use of thermometers, you are interested in the temperature of some specific objects. Anything outside the system, outside this particular object you're interested in, which has an effect on the behavior of this particular object you're interested in, that is what we refer to as the surrounding or the environment. So the surrounding or the environment has an effect on what the system does. Okay, so basically that's that about temperature. You want to measure the temperature of some specific object. Okay, that specific object whose temperature you want to measure is what we refer to as a system, and anything which is in close contact with that particular system whose temperature you are not interested in, we group them and we say they are the surrounding. Okay, now for you to measure temperature, you need to use a thermometer. Okay, the thermometer is a device you use to measure the temperature of a particular object, and there are different types of thermometers which are in use around the world. Basically, any thermometer has got this property which depends on temperature. For example, liquids which are used in thermometers, which we use in hospitals and also in the labs to measure temperature, those liquids, when they come in contact with something which is very hot, then they expand. So liquids used in thermometers depend on the expansion. They depend on a property called thermal expansion. You can also have a thermometer which depends on voltage, as in the case in the thermocouple, because in the thermocouple you have to join two different metals into a junction, and the voltage difference is what is translated into thermometer. So you can build a thermometer which is based on voltage, because the voltage depends on the thermometer. The hotter it is, then you're going to have a different voltage. And you can also have another kind of thermometer which is known as a resistance thermometer. A resistance thermometer uses the fact that the resistance of a conductor is going to increase as the temperature increases, almost linear. Okay, so in a nutshell, regardless of whichever way a thermometer works, if you want to measure the temperature of a particular object, a system, you need a thermometer of one form or the other. And there are a couple of common types of thermometers which are in use. One of them is what is known as a liquid in glass thermometer. Liquid in glass thermometers basically exploit the fact that a liquid is going to expand when it gets hot or when it is in contact with something which is hot. And there are different types of liquids which are used. One of the liquids which is used is mercury. Mercury is a liquid metal, but you can also have alcohol. The alcohol, when it gets heated, it expands. Okay, but the alcohol is most of the time alcohols are colorless. So what actually happens for you to use an alcohol in a thermometer, like in this particular thermometer which has been shown here, you need to color the alcohol. So the alcohol has to be given certain color so that you can easily see the expansion of the liquid in that particular thermometer which is being used. So basically you've got the liquid in glass thermometer, and this liquid is sealed in a bulb here, in this bulb, and when the temperature increases, the liquid is going to expand, and as it expands, its volume increases and it's pushed along this tube, this capillary tube, like that. So the thermometer, usually the liquid in glass thermometers, have got markings, and these markings, somehow we have decided that these markings are going to represent certain readings of temperature. So basically that's how it works. So if it gets cold, the liquid is going to contract. If it gets hot, then the liquid expands and it gets pushed along the tube, like that. So basically, yeah, liquids expand as the temperature rises. Therefore, the temperature, as the temperature rises, this liquid is going to expand and it will be pushed along the capillary tube, which is very thin. So the liquid itself in the bulb might expand very little, but it is being forced into an evacuated capillary tube, which is very thin and has got markings. So we can actually see, compared, say, oh, it looks like it is at this particular temperature, value of temperature. There is also another thermometer which is commonly used, and that is what is known as a gas thermometer. In this particular case, you have a gas which is filled in a tube, in a bulb, or in a bottle. You have a gas in a bottle or in a bulb. Then that gas in a bottle or in a bulb is connected with flexible tubes, and those flexible tubes are connected to a U-shaped manometer which is filled with mercury. So the operation of a gas thermometer is basically such that when the gas in the bulb or tube, the bulb which is filled with the gas is put, like in this case, it is put in a bath of a substance whose temperature we want to measure. So depending on how hot or cold that particular substance is, the gas is going to expand. As the gas expands, it is going to push against the mercury column here. So depending on the expansion in the pressure of the gas, then there's going to be one of the columns, the left side of the left side of the U column of the U tube is going to be pushed down, and the other one is going to be pushed up, and we will be able to measure the difference in heights in these columns. This difference in heights in these columns can be translated into pressure using the formula pressure is equals to rho, which is the density, the acceleration due to gravity, rho gh, where rho is the density of the mercury, g is the acceleration due to gravity, and h is the height of the column. So basically, we can somehow translate the pressure of the gas as we put it in something into a value of temperature, and that is the basis of a gas thermometer. So basically, we've got gas thermometers, and with the advent of COVID-19, you have seen use of a new kind of thermometer, which is a contactless thermometer like this. So basically, these contactless thermometers are actually a kind of thermocouple, but without wires. There is no contact, and you can use them to measure temperature. And these things are being used at the hospitals, at the airports, and at malls, so that we check your temperature to see if you've got a fever when it comes to detecting and tracing which persons or people have got COVID-19. So the use of these ones, they have been used before, but their use has become more prominent now with this whole outbreak of COVID-19, which we are all experiencing around the world. So basically, in a nutshell, you have, when it comes to types of thermometers, you've got liquid in glass thermometers, then you've got gas thermometers, then you have these ones, thermocouples, contactless thermocouples, which are now being used to measure temperatures of people. Now, the way a thermometer works really, for a thermometer to be useful, one thing you need, thermometer basically serves two purposes. One of the purposes of a thermometer, why you want to measure the temperature, is because you want to find out if one body has the same temperature as the other body. Okay? You want to find out if one body has got the same temperature as the other body. That is one of the reasons why you want to measure temperature. You want to find out if 2 or 3 different things actually have the same temperature. Okay? The other thing is maybe because you just want to find out how hot or how cold something is. And that is going to require numbers. Okay? Your thermometer, in one way or another, when it measures the temperature of that particular object, there has to be a way that thermometer is going to translate whatever it is measuring into a number of temperature. So for you to do that, for a thermometer to give you a precise value of temperature, you have to do a process where you put markings on these thermometers. Okay? That process is what's known as calibration. You have to calibrate thermometers, and you have to use certain conditions which are known as fixed points, which anybody around the world, which are available to everybody, and around the world, those conditions are easily reproducible. So a fixed point, a good fixed point really should be available to anybody around the world, that is global, and it should be easily reproducible. And for any thermometer, you need 2 of these fixed points. You need 2 of them. Okay, so once you have the fixed points, then somehow, as we are going to see, depending on the type of thermometer, there is a way you go about marking these fixed points. Then after you get your fixed points, then you put the marks in between, then you get your temperature. Okay, the first thing really you want to do with the temperature with the thermometer is you want to find out if 2 or more different objects have got the same temperature. That's what you want to find out. Does this object and that object actually have the same temperature? Basically, that's the first thing you want to do. Okay, and how do we know that 2 or more objects have the same temperature? Well, let's take a case of people who go to the hospital. Patient A goes to the hospital and patient B goes to the hospital. Then they go to the nurse, and the nurse has to ask them they wants to find out what the temperature is. So the nurse is going to get a thermometer, probably put it most likely in the armpit of the first patient. Then we wait for 3 minutes. Then after 3 minutes, the nurse is going to retrieve the thermometer from the armpit of this particular patient and see what the reading is on that particular thermometer. Then after seeing what the reading is, the nurse is going to record that particular reading. Let's say, for instance, maybe 37 degrees. Okay, then he will wipe the thermometer, then get the same thermometer, give it to the second patient. Again, put in the armpits of the second patient. That particular second patient will put the thermometer in the armpits, or his or her armpits, then wait for 2 minutes. Then after the 2 minutes, again, the nurse is going to retrieve that particular thermometer. Now, imagine, for example, in this particular case, where the reading on the thermometer of this other second patient is also 37 degrees. Then what does the nurse conclude about the temperatures of these 2 particular patients? Using a third object, which is the thermometer, the nurse is able to get the temperature of the first patient, which is 37 degrees. Using the same object, the nurse is able to get the temperature of the second patient and gets a temperature of 37 degrees. By getting a 37 degrees on the second, the nurse concludes that patient A and patient B have got the same temperature. By comparing what the reading is. If the reading on the thermometer is the same, then we conclude that patient A and patient B have got the same temperature. And that is the basis of the Zeroth Law of Thermodynamics. The Zeroth Law of Thermodynamics basically, in a nutshell, tells us that if you have an object, you get its temperature, then you measure the temperature of another object, then the temperatures are the temperature reading is the same, then we conclude that those 2 particular objects are at the same temperature. So the first thing really, before you go wondering whether this guy is hotter than the other, what you actually want to find out is if the 2 of them, object A and object B, are at the same temperature. If at the same temperature, you will see from the marking. Otherwise, if they are not at the same temperature, then your thermometer is going to show you different temperature readings. Okay, and that is basically the basis of the thermodynamic law, the Zeroth Law of Thermodynamics. And in a nutshell, this is what it says. It says 2 objects that are in thermal equilibrium with a third object are in thermal equilibrium with each other. 2 objects that are in thermal equilibrium with a third are in a third object are in thermal equilibrium with each other. Now, thermal equilibrium basically involves a condition where the temperature of the thermometer becomes steady, becomes constant. If you get a thermometer, you put that thermometer in your armpits. In the first minute, the liquid in the thermometer is going to expand. It will continue expanding and it will reach a certain level where the liquid no longer expands, it becomes steady. When the thermometer reading becomes steady, then we say that the thermometer and the object whose temperature it is meeting are now in thermoequilibrium. So, if you use a thermometer to measure the temperature of one object, and you are only going to get that temperature after the column of liquid in the thermometer has stopped changing, then you know that there is thermoequilibrium which has been achieved. Okay, so if you use a thermometer, which is the third object, you use a thermometer to measure the temperature of that particular other object, and you also use the same thermometer to measure the temperature of another object, and the temperature is the same. The temperature reading is the same. Two objects that are in thermoequilibrium with the third are in thermoequilibrium with each other. Then we conclude that these other objects, object A and object 1 and object 2, through object 3, with the use of object 3, which is the thermometer, we conclude that these particular objects have the same temperature. Okay. So apart from having the same temperature, the next thing really you are interested in, depending on the kind of thermometer you have, is you want to find out, you want to have a precise value. You want to have a precise value of temperature. So if you have manufactured a thermometer, a liquid glass thermometer like this one, without any markings, you have manufactured this, you have added the liquid inside. The next thing you do is you need to calibrate the thermometer. You need to put markings on it. And how do you do that? You choose two fixed points. One of the fixed points you choose, which is easy and available to a lot of people, is you use water, a mixture of water and ice. Nearly everybody around the world who is serious can afford water and ice, a mixture of water and ice. So you get this thermometer, you dip it in a mixture of water and ice, and you let it be there for some time. So the liquid in the thermometer is going to expand to some level, some height. The liquid in the thermometer is going to expand to some height as you have dipped it in this mixture of water and ice. The level to which the liquid in the thermometer is going to, the height to which the liquid in the thermometer is going to expand, that is what we postulate to be the 0 degrees. Okay, it is postulated, suggested, that's what we suggest to be 0 degrees. Whether the temperature of water is actually equals to 0 degrees, well, we don't know. People just decided that it's going to be 0 degrees, so it becomes 0 degrees. Okay, then after marking the 0 degrees mark on the thermometer, next we get this ice and water, we put it in a stove. Okay, then we boil the water and the water begins to evaporate. Then we dip in the thermometer. When we dip in the thermometer, the water, the liquid in the bulb is going to get heated and it will expand. It will expand to a certain height. Okay, that height it's going to expand to is what we take to be 100 degrees. Again, whether water is boiling at 100 degrees or not, it is all up for debate whether that is actually 100 degrees. Okay, so we put it there, then we mark that to be 100 degrees. Okay, so on this particular thermometer, we have 2 points. We have marked 2 points. We have marked the freezing point of water, which we have given a value of 0 degrees. Then we have also marked the boiling point of water, which we have also given a value of 0 degrees. This is without regard to how the water is expanding in between here. Then the next thing we do is we divide this space, we divide the space between the 100 degrees mark and the 0 degrees mark we divide it into 100 equal parts. The space between the 0 degrees mark you have put at the bottom and the 100 degrees mark you have put at the top, we divide that space into 100 equal parts. When we divide that space into 100 equal parts, each of those parts becomes what is known as 1 degree. So with this kind of thermometer, you can only measure temperatures values between 0 degrees and 100 degrees. Above that and below that, it's kind of a problem. You can't do that. Okay. And this kind of a thermometer where the marking between the first mark, the fixed point, the lower mark, and the upper mark is divided into 100 equal parts, that is what's known as the centigrade scale. The first person to come up with this centigrade scale is a Swedish scientist known as Andreas Celsius. And sometimes this centigrade scale is referred to as the Celsius scale. Okay. He first proposed that in 1742. There is another German scientist, Gabriel Fahrenheit. He also came up with a kind of Celsius scale, a kind of centigrade scale, a scale where the lower point and the upper point are divided into 100 equal parts. In his case, the lower point was the freezing point of salt water. The freezing point of salt water. That was what was marked as the lower point. In the Celsius scale, the lower point is the freezing point of a mixture of water and ice. In the Fahrenheit scale, the freezing point, the lower point is the freezing point of salt water. Then the upper point is the temperature of the human body. Okay? So the lower point, he suggested that the lower point is supposed to be what is known as 0 degrees Fahrenheit, and the upper point is what is supposed to be known as 98. The upper mark is supposed to be given a value of 98.6 Fahrenheit, and in between here, the 0 degrees and the 98, there were 100 equal parts. Okay, now the problem really, these thermometers work. They know how to predict the liquid in glass thermometers work. They know how to predict the freezing point. They know how to predict the boiling point of water. The problem with liquids is that liquids have got a funny behavior when it comes to expanding. They don't expand at the same rate at all temperatures. The rate of expansion for a liquid is not always the same. For example, water has got some abnormal expansion at around 4 degrees. It expands in a funny way. Okay? And like that. So, as much as these thermometers are rigged to properly predict the 100 degrees, in the case of the Celsius scale, it's properly rigged to predict the 100 degrees temperature and the 0 degrees temperature, it might not reliably predict the temperatures in between here, even after we have divided the space between the 100 degrees and the 0 degrees. We have divided the space into 100 equal parts. The division of the spaces into 100 equal parts assumes that the liquid expands at the same rate throughout this range. But liquids don't do that. Liquids have got their funny way of behaving. Therefore, the temperatures in between here might not actually agree with whatever is supposed to be happening. Okay. And that brings us to this gentleman here, the constant volume gas thermometer. That brings us to this one. So basically, in this case, for a constant volume gas thermometer, you have a gas, and this gas is very, very dilute. Okay, then you put this gas, you put it in a bulb, then you connect the bulb to some tubes, and those tubes you connect them to a manometer, a manometer which contains, in the tubes, contains mercury. So basically, this is the kind of arrangement you have. Then if you want to measure the temperature with a gas thermometer, you submerge the tube which contains the gas in the particular thing, environment, whether it is a liquid whose temperature you want to measure. Okay? Now, again, this one also needs calibration. The gas thermometer needs to be calibrated. So the first thing you actually do is you submerge the gas thermometer. You submerge your gas thermometer in ice, a mixture of ice and water, pure water and ice. You submerge your gas thermometer, not a mixture of ice and pure water, okay, at a condition which is known as the triple point. A triple point is basically a condition where the water, ice, and gas coexist. The triple point of water occurs at a temperature of 0.01 degrees, very close to 0 degrees. So when you get this gas thermometer, the bulb, you submerge it in a mixture of ice and water. Then hopefully you get on this triple point. You compare, for the triple point, you compare what is the value of the height, this height. As you submerge in this mixture of ice and water, what is this height? This height, the value of this height between the two columns, excuse me, the value of the height between the two columns is what's going to give you the pressure. So from the height, you can predict what the pressure is going to be. And this whole arrangement is also a constant volume. The volume is the same. Okay? The volume of the gas you put in is the same. The only thing which is changing is the pressure. So you multiply the volume times the pressure, it gives you this PV. So for that particular temperature where you mix, you put your bulb in a mixture of water and ice, you find out what the product of pressure and volume is. So you have a plot like this. You have a plot of temperature at the bottom, and on the y-axis you have a plot of pressure multiplied by volume, a product of pressure times volume. So for each of these guys, at the triple point of water, you mark what the pressure is, then you multiply the pressure times the volume, then you get yourself PV. So you mark that, whatever it is, for a particular gas. Then next, you submerge this gas, this thermometer, the bulb, in boiling water. Okay? Again, the gas is going to expand. It will exert a pressure on the mercury column. So this left-hand side of your mercury column is going to be pushed down. This left-hand side. The gas is going to push down like this, which is going to increase the height of the difference in height of the two columns. That results in an increase in pressure. So the pressure is going to increase. Okay? The pressure will increase, and of course the volume same. So you multiply the pressure and times the volume, then for a particular gas you get a point on this graph for that 100 degrees. We again we are being suggestive again. We are being suggestive to say we think at the triple point of water the temperature is 0 degrees. Again, we are doing guesswork to say at the boiling point of water we postulate the temperature to be 100 degrees. Then we make a mark on this plot. The next thing we do after making those points, this particular point and that particular, we join these points by straight lines. You can change the gas you're using. Okay, you can use a different gas. If you use a different gas, you submerge the bulb in water, a mix of water and that, and also boiling. You are going to have different lines for different gases. Now, this is where the interesting bit happens. You get these lines, then you extend them backwards. these lines, for each of the gases, you extend them backwards. When you extend these lines, they are going to cut the temperature axis at the same temperature of minus 273.15. I've written 16 here, kind of a mistake. I really get confused whether it's 273.1615. But they are going to hit the temperature axis at this point. It doesn't matter which gas you're going to use. As long as you have rigged the triple point of water, and also you have rigged the triple point of water, then you have set the triple point of water to say this is what's going to be 0 degrees, and also you rig the boiling point of water, and you set the boiling point of water to be 100 degrees. Then you extend, then you join these lines for the first gas, for the second gas, for the third gas. You join those lines, then you extend the lines backwards. Okay, these lines are going to meet at that particular point, regardless, independent of what kind of gas you have used. So it appears as if there is a point where all gases agree. That's where they're meeting there. Okay, so in this temperature scale, the temperature scale we're about to come up with, which is known as the absolute temperature scale or the Kelvin scale. In this temperature scale, this point where the gases are meeting here, this is what becomes our zero. If this point becomes zero, then what is 0 degrees Celsius here becomes 273.15. Then the 100 degrees becomes 373.15 degrees. Okay, so we kind of shift. We start from here. Instead of being minus 273.15 or 16, this point becomes 0 Kelvin. We set this to be 0 kelvins. If this becomes 0 kelvins, then what is 0 degrees Celsius here becomes 273.15 kelvins. Then what is 100 degrees here becomes 373.15, like that. Okay, next, the space between this point. How do we determine what is 0 Kelvin, what is 1 Kelvin? The space between the 0 degrees point here and the minus 273.15 degrees kelvins is divided into 273.15 equal parts. 273.15 equal parts. How exactly that is done, I am not really sure. Kind of don't have the expertise to explain that. So each of those divisions becomes equal to 1 Kelvin. And basically that's how the Kelvin scale works. So you divide the space between the minus 273 and the 0, you divide it into 273.15 degrees points. The reason why you're using the 0 here, it's because you use the triple point of water. The triple point of water is 0.01 degrees. If it's 0.01 degrees, then you have that as the 273.15 degrees, like that. The triple point of water is fixed. The triple point of water does not change. It is an actual fixed point. And this point where all these lines are meeting is also an actual fixed point. It doesn't change regardless of any change in conditions. So these 2 points where these lines are meeting and the triple point of water are actually proper fixed points. So we use those ones, then we divide the space between the minus 273.16 or 15 and 0 degrees, the 0.01 degrees, which is the triple point of water. We divide them into 273 equal parts, and each of those equal parts becomes what we call a Kelvin. And that is how you form this temperature scale, which is known as the Kelvin scale. And in a nutshell, so we end up with something like this. Where the lines meet, that becomes a 0 Kelvin, and what was the 0, what was your triple point of water, your 0.01 degrees, becomes your 273.16 or 15 kelvins mark, like that. So depending on where the product is, when you use a gas thermometer, you see what the pressure is, you multiply by the volume. Depending on what particular mark where you are, you come down like that, then you'll be able to get your temperature in kelvins. Then later on, you can change your temperature in kelvins to degrees Celsius. And basically down here, the same thing which you have here, that's the same thing. Now this is just generally for any gas, since it doesn't really matter what kind of gas you have. It will still meet at this particular point there. It ends at that particular point, which is our 0 kelvins, and this other point here, this is the triple point of water there. Okay. And if you want to change the temperature from kelvins to degrees Celsius, basically this is the formula you use. From degrees Celsius to kelvins, that's you use equation number 1. From kelvins to degrees Celsius, use equation number 2. Okay, so basically that is about temperature. Okay, now the one thing you will notice, one thing about these gases, regardless of the gas you're using, it's a straight line which ends up there. And since it's a straight line, and we know straight lines, we know how to describe a straight line. You can describe a straight line using y is equals to mx. Now in our case, what is on the y-axis is your product of pressure times volume, and what is on the x-axis is the temperature. So basically, you can describe this line in the form of a straight line as PV equals to C, which is your slope, multiplied by your x, which is the temperature, like this. So you can describe the line on the gas thermometer you use for calibration, the calibration line on the gas thermometer, to be this: PV is equals to C times T. The P is the pressure, the V is the volume, then the T is the temperature, and C is the slope or the proportionality constant. Okay. From experiments, extensive experiments which have been done by people in the past, we know that this C is actually equals to N, and this thing called Kb. The N is the number of atoms of the gas in the gas thermometer, and the Kb is a constant known as Stefan-Boltzmann constant. Okay. Here, so the Kb is a Stefan-Boltzmann constant. The N is the number of atoms which you have there. Then next, from the number of atoms which you have there, you can express the number of atoms in terms of a number of moles. So basically, the number of moles is equal to the number of atoms divided by Avogadro's number. Avogadro's number is the number of atoms you have in 1 mole. So whatever number of atoms you have in that particular container or bulb of the gas thermometer, you divide it by Avogadro's constant, it will give you the number of moles. Therefore, you can express the number of atoms in terms of the number of moles times Avogadro's constant. So instead of writing N here, instead of writing this N, we tend to write this, the number of moles multiplied by Avogadro's constant. Then we substitute in here, so we end up having PV is equals to small n, then then Avogadro's constant, then Kb, then T. However, this Avogadro's constant times the Boltzmann constant, that is also equal to another constant which is referred to as the gas constant, R. R is equals to Na times Kb. Na, we know what Na, Avogadro's constant. Avogadro's constant is 6.022 times 10 to the power 23 multiplied by Kb, which is 1.4 times 10 to the power 23 joules per Kelvin. That you multiply, that gives you a gas constant which is equals to 8.314 joules per mole per Kelvin. Okay, R. So if we replace these guys, you end up with R here, and if you put back the R here, you end up with PV is equals to N, the number of moles, the gas constant times the temperature. Any gas, now this equation PV is equals to nRT is what is referred to as the ideal gas law. Any gas which obeys this law is referred to as an ideal gas. Usually an ideal gas is very, very dilute. Atoms in an ideal gas are far away from each other and they do not feel any force of attraction between them. The only kind of interaction atoms in an ideal gas feel is when they collide. Okay, that's when you've got something happening between the atoms of an ideal gas. Otherwise, that's what we have, an ideal gas. So basically, what we are interested in when it comes to temperature and stuff, we kind of tend to study an ideal gas. Okay, and that equation is going to come back a lot. This equation, in your study of temperature and thermodynamics, this equation is going to come back a lot. The next thing we're going to look at is we try to describe. Remember at the beginning, I said, in layman's terms, you can describe temperature as the degree of hotness and coldness, but we can do much better than that. Okay, it is possible to do much better than that, and that is where this guy comes in, the kinetic theory of gases. Okay. This theory helps us to explain exactly what temperature is. Now, in order to do this, we consider a cube which has got length size of L times L times L, basically a cube of equal sizes, equal lengths. Okay, so this cube has got each side having a length of L. Then next, we kind of consider that this cube is filled with gas atoms, and there are n of these gas atoms, and all these n gas atoms are moving in random directions, basically like that. Now, if things are moving in random directions, it quickly becomes very difficult to do any meaningful physics. So, we make some assumptions. Okay. The first assumption we do is we divide these gas molecules into groups. Okay. We say atoms are actually not moving. Yes, in the reality they are moving in random directions, but we kind of say not quite. We allow some of them to move only from left to right, then we allow some of them to move only up and down, then we allow some of them to move in and out of kind of like the page of this computer or the page of the book. So basically, the n atoms which we had, we divide them into 3 equal groups. Each group has got n divided by 3 atoms moving left to right, the other n divided by 3 moving up and down, the other n divided by 3 moving in and out of the page. That's the first assumption we make. So we make sure we account for all the atoms, where they are, which directions they're moving. The next assumption we make, we know that as things are moving randomly, they end up moving at different speeds on their own. So we conclude, say, not quite like that. So we say, actually, let us just say all the atoms are moving with the same speed, v. It is an oversimplification of reality, but it makes life very, very easy. Okay, so those are some of the assumptions we make. We assume we divide our atoms into groups. There are n of them. We divide them into groups of n divided by 3. Then also we also make another assumption that they are moving with the same speed. Okay, so if they are moving with the same speed, now we look at the case of one atom. If an atom is moving, then it hits the wall, it's going to bounce. Okay? If an atom is moving, it hits the wall, it's going to bounce. We have said that these atoms are moving with the same speed. So the velocity of the size of the velocity of these actual things is actually the same. However, the atom has changed direction. The change in direction constitutes acceleration. If you are moving with the same speed, then you turn back and start moving backwards the way you came. even if you're moving at the same speed, then you have accelerated, because acceleration is a vector, and a vector has got size and magnitude, has got size and direction. As much as the size has not changed, the direction has changed, and that constitutes acceleration. Okay, so what really we want to do is, in a nutshell, the whole game plan here is we want to find how much force those atoms are exerting on a wall. So the way we're going to do it, we are going to find out how much force one atom exerts on a wall. After we find out how much force one atom is exerting on a wall, we'll find out how much force n divided by 3 atoms which are allowed to hit that wall will exert, how much average force. Once we know the average force which is being exerted by these atoms on this particular wall, we are going to divide that force by the pressure. Sorry, we're going to divide that force by the area. That is going to give us the pressure which is exerted on that particular force. And we'll proceed like that. So basically, in a nutshell, that's what we want to do. First of all, we want to find the force due to one atom. Then later on, we want to find the force due to n over 3 atoms. Then after that, we want to find the pressure exerted by those n over 3 atoms on that particular wall, and we'll move on from there. So here, we pick an atom moving towards the wall. Okay? An atom moving towards the wall, that is a particular direction. Then an atom will also be coming towards us. When it hits the wall, then it comes back towards us. That will be another particular direction. Now the choice we make is, as the atom hits the wall and comes back towards us, that will be our positive direction. So if the atom is approaching us, that is positive. Then by implication, it means that as the atom is moving away from us, that is going to be negative. So what we want to find is the change in momentum after the atom leaves one end, hits the wall, then comes back. Okay? And we have assumed that these atoms are moving with the same speed. So as the atom is going, then it hits the wall, it will still be moving with the same speed as it comes back. The only thing which would have changed is the direction. So we want to work out what is the change in momentum after the atom hits the wall. So the change in momentum is going to be the final momentum minus the initial momentum. The final momentum is the velocity with which the atom is approaching us after it hits a wall, which is mv, v being final, minus the velocity with which the atom is going away from us. We have chosen the direction coming towards us to be positive, meaning that as the atom is going away from us to hit that wall, it has got a velocity of minus v. That minus v times the mass of that atom, that gives us this quantity minus mv. So basically the change in momentum is going to be equal to mv minus mv. That gives us a change in momentum of 2mv. So an atom which is moving with a constant velocity of v, when it changes direction and starts coming towards us, experiences a change in momentum of minus 2mv. Next, we want to find out how much time it takes the atom to move from here where we are towards the wall and come back. Now remember, these atoms are moving in a cube, okay? And each cube, the size of each cube is L. So as the atom is going, it covers a distance of L. When it comes back, it covers another distance of L. So altogether, as the atom goes and comes back, it covers a distance of 2L. Okay? Then, in this distance of 2L, the atom is moving at a constant speed of L. Therefore, we can find out how much time the atom took to leave this end, go and hit the wall, then come back. And that's what we have here as 2L. The total distance traveled by the atom is 2L divided by the speed at which the atom was traveling, which is v. That gives us the time. With the time and the change in momentum, so we have the change in momentum. The change in momentum is 2mv. Then the time taken for this change in momentum altogether is 2L over v. We can work out the force which one atom exerts on the wall of this cube. the force is going to be equal to the change in momentum divided by the time, which is equal to 2mv divided by 2L then v, which is equals to 2mv squared. This v goes on top, so you end up 2mv squared divided by 2m. Then you've got a 2 and a 2, the 2 and a 2 on top, and at the bottom they cancel out. You end up having mv squared is equal to mv squared divided by L, like that. Next, this is a force exerted due only to one atom. Next, you want to find out the force exerted due to the n divided by 3 atoms. Okay, so in that case, it's going to be equals to the force due to one atom multiplied by the number of atoms which you have going against that particular wall, which is n divided by 3. So you end up having n over 3 times the force due to one atom, which is equals to here n over 3, how many atoms you have, times the force due to one atom, which is mv squared over L. That gives you n mv squared over 3L. Okay, this is a force. Then after that, so now we have the average force exerted by all the n over 3 atoms on a particular wall. Okay, then you divide that force. So here, this is supposed to be for the force. You divide the force by the area of that particular wall. This here is a mistake. It's supposed to be the force. So you divide the force by the area on the wall. So the force, the average force due to the n over 3 atoms divided by the area on the wall. The wall has got the wall of the cube has got length LL, which means the area is equals to L squared. So this L squared, then that, you end up having 3 L squared, then n mv squared, like that. Now this L squared is actually the volume of the cube. The L squared is actually the volume of the cube. So you end up having pressure to be equals to the number of atoms, then the mass of each atom, the velocity squared divided by 3v. You multiply by v, the volume on both sides, you end up having PV is equals to n mv squared divided by 3. Now remember from the ideal gas law that PV from the ideal gas law, pressure times volume is equals to the number of moles, the gas constant times T. So this PV which we have, when we apply the gas law, when we enforce the gas law, is also equals to the number of moles R and T. So we equate these guys, these two equations, equation number 19 and equation number 20, they don't look the same, but basically they're equivalent. So we equate, we force this equivalence, so we end up having PV is equal to n mv squared over 3, which is equal to n RT, like this here. So that basically end up having this. We end up having we end up having like that. You end up having n mv squared divided by 3, then n RT. We multiply on both sides by 3, we end up having n mv squared. There is a mistake here. There's a cubic here. This cubic is supposed to be actually 2. So there's a mistake there. There's a cubic which is supposed to be actually 2. So you end up having n mv squared, then 3n RT, like that. Then you divide both sides by 2. When you divide both sides by 2, you have n mv squared divided by 2, then 3n RT divided by 2. Now, you remember something, say, actually the number of moles is given by this. The number of moles is equal to the number of atoms divided by Avogadro's constant. And also, the gas constant is equal to the number Avogadro's constant times Kb. So you make the substitutions. When you make the substitutions on the right hand side, you end up having the number of moles, the mass of the atoms, the velocity squared of the atoms over 2 is equal to 3 n over a, then n kb, then t. So here the n over a times that cancels out. So you end up having 3, then you've got an n, then you have got a kb, then you've got a t and a half. Then there's n this side, and there's n that side. So you cancel out the n's, you end up having m v squared over 2 is equal to 3 kbt over 2, like this. Now, this expression, mv squared over 2, this is actually the kinetic energy of the gas. So, the average kinetic energy of the gas atoms. So, basically, what we are saying is the average kinetic energy of the gases atoms, which is equals to mv squared over 2, is equals to 3 over 2 kb. This expression, which I have rewritten here, gives you the meaning of temperature. The temperature of a gas, or the temperature of anything, the temperature of a gas or the temperature of anything actually tells you, carries information about the kinetic energy of the atoms in that particular thing you are studying, in this case a gas. So the temperature actually is not just the degree of hotness or coldness. That hotness or coldness you feel when something is very hot, it is because the atoms of that particular thing, which is very hot, are hitting against your skin. That's why you feel the heat. On the other hand, if it's very cold, then if the kinetic energy is very low, then you end up having a temperature which is low. Okay. Therefore, this helps us to also define something which is known as absolute zero. If the kinetic energy of the atoms vanishes, if the kinetic energy of the atoms becomes zero, Ke becomes zero, these guys, 3 is a number, 2 is a number, it can't become zero, Kb is a constant, it can't become zero. So if the kinetic energy of the atoms becomes zero, then the temperature has to become zero. So this gives us a definition of this point. This point we have on the graph, the 0 Kelvin point. Where is that? This point, 0 Kelvin. At 0 Kelvin, your gas atoms have got no kinetic energy. They have stopped moving. They are motionless. Okay. Your gas atoms have stopped moving. They are motionless. At any other temperature, your gas atoms have got kinetic energy. This also, as a consequence, also tries to help us understand what we mean when we say two bodies are at the same temperature. If two bodies are in equilibrium, yes, we know that they are at the same temperature. What does it mean when things are at the same temperature? If things are at the same temperature, from this equation, if the temperature is the same for two different bodies, it means that the average kinetic energy of the atoms in that particular gas or body is the same. If two bodies are at the same temperature, it means that the average kinetic energy is the same. Okay. So one, at absolute zero, where the temperature is 0 Kelvin, the kinetic energy of the gas atoms is equal to 0. At any other temperature between two different bodies, which we think these bodies are at equilibrium or have the same temperature, then at that particular temperature, those bodies have got the same value of kinetic energy. Okay. Next, what else do? We proceed to rewrite this. Okay, so we know the kinetic energy part, this equation, we can rewrite it like this. This gives us mv squared divided by 2, which is equal to, that's a kinetic energy 3 over 2, then kbt, like that. Now, this velocity, v squared. Now, remember that at the beginning, we decided to say we are going to have a certain value of atoms going from left to right. We are going to have a certain value of atoms moving up and down. We are going to have certain atoms moving in and out of the page. Basically, that is the X, the Y, and the Z directions. We can rewrite. So basically, in each of these directions, this bunch of atoms have got their own values. From left to right, we can say that is the X direction. From up and down, we can say that is the Y direction. From in and out of the page, we can say that is the Z direction. Okay. So in each of these directions, these atoms have got their own amount of velocities. So those velocities, we can rewrite them using this. Velocity v squared, we can write v squared to be vx squared plus vy squared plus vz squared. Then we expand, equals to that, we end up having half mvx squared plus half mvy squared plus half mvz squared, which equals to, then we can rewrite this, there's a 3 there, so we can write it as half kbt plus half kbt plus half kbt. So in each of these directions, we can write, say, the velocity, the energy of the atoms along the x direction will be equals to, which is half mv squared is equals to half kbt squared. So in each direction, we have allowed the atoms to move. We actually can find out how much energy they have and how that is related to the temperature. The other thing we can do is, from this equation number 29, there's a 2 at the bottom, there's a 2 at the bottom. We can cancel out those 2's. If we cancel out the 2 at the bottoms, then we end up having m v squared is equals to 3 kbt, like this. Then we divide by 2 by m on both sides. We remain with v squared is equals to 3 kbt over m. When we square both sides, we end up with a value of velocity v, which is equal to the square root of 3 kbt over m. And this value of velocity is what we refer to as the root mean square velocity. Basically, this is the velocity with which an atom which has got average kinetic energy has. An atom or a molecule which possesses average kinetic energy, it is going to have a value of velocity which is known as VRMS, the velocity root mean square, or the root mean square speeds. So basically, in a nutshell, this is what temperature is. Temperature is a measure of the average translational kinetic energy of the atoms which make up this particular system whose temperature you want to measure. The total translational kinetic energy, as these atoms are moving back and forth, their average translational kinetic energy, that is what temperature is. Okay, we come to an end. All right, we finish.